Welcome to the third video in our Class 15 series of lecture videos. We'll talk a little bit more about the solvent effects in SN1. So we will never see an SN1 reaction in hexane or any other non-polar solvent. The solvent's purpose in an SN1 reaction is to stabilize the transition state of the rate determining step. And by stabilize the transition state, what I mean is it lowers the activation energy so the reaction can go faster. A polar protic solvent is better to solvate charge-separated species than a polar aprotic solvent. Why? Well, there are stronger solvent-ion interactions for the polar protic solvent than there is for what? Solvent-ion interactions for a polar aprotic solvent. So for example, let's say we have our tert-butyl bromide and we're in water. We're doing an SN1 to get to our tert-butyl alcohol and HBr. Our relative rate is 400,000 times faster than when we are doing the same reaction in acetone with 10% water. Of course, water ends up as part of the product, but here we'll have acetone, much more statistically likely to be around our reactant, so it does not as easily break in to the carbocation, so it doesn't undergo that first rate limiting step as easily. And so, wow, 400,000 difference. Secondary alkyl halides can also do SN1. They are just slower. So here we've got isopropyl bromide and water. We're forming isopropanol and HBr through an SN1 mechanism. The relative rate is 1 compared to what? Compared to tert-butyl bromide, so our 2-bromo-2-methylpropane in water forming tert-butyl alcohol and HBr, that relative rate is 1,000,000. So why? Why do tertiary alkyl halides or tertiary carbons go faster in an SN1 reaction? And that has to do with carbocation stability. Tertiary carbocations are more stable than secondary carbocations, are more stable than primary carbocations, are more stable than methyl carbocations. For the purposes of our course, we don't see methyl or primary carbocations. We will see primary carbocations next semester when we talk about allyl groups and benzyl groups. Secondary alkyl halides can do both SN1 and SN2. They're the kind of strange electrophiles. So you need to think, what conditions favor SN2 over SN1? Well, polar aprotic solvents, first of all, and then small charged nucleophiles. So methyl halides or primary alkyl halides do not undergo SN1 since it is more difficult to form methyl carbocations or primary carbocations than it is to form secondary and tertiary carbocations. So we remember why tertiary carbocations are more stable. It has to do with the fact that they have more hyperconjugation than secondary or primary carbocations, unless you're alloic. So for a last note in this lecture video, I wanted to talk about additives. Sometimes additives can assist with carbon halide bond cleavage or heterolysis. Here we've got our tert-butyl bromide and ethanol forming ethyl tert-butyl ether. And we'll go ahead and throw in some silver nitrate. And hopefully we don't get it on our hands because we'll get little black spots if we get it on our hands. But the silver can, of course, form an insoluble precipitate with the bromide. So silver bromide is insoluble. That removes it from the homogeneous solution, and of course Le Chatelier, right, we help drive it to the right. And instead of forming HBr, we're forming nitric acid. So the silver can sort of help tug on that bromine to form silver bromide, and our carbocation that lowers the activation energy as well, and so our reaction is going to go faster too. So, and of course, in the mechanism, once you form the tertiary carbocation, your ethanol will take a pair of electrons from the oxygen, use them to form a bond to that empty p orbital on the carbon. Then all we need to do is deprotonate the ethanol molecule that added in. So we'll take a molecule of ethanol instead of the nitrate anion, because the molecule of ethanol is more basic than the nitrate anion, and we'll get protonated ethanol and the nitrate anion, which is really what happens to what? Nitric acid, HNO3, in your ethanol solvent. So that concludes this last lecture video, right? And of course, that last dissociation reaction is shown below, nitric acid dissociating ethanol, right? We favor the right side of this equilibrium, which really means ethanol is more basic than nitric acid.